And I'll share the screen. And we're now to a point where I don't believe, need to look at this anymore. So I'll minimize that and maximize this. We might need to pull out an S value, but we can always bring that back up if we need to. And see, these are my old lecture notes, and was the problem that I first started with, but it gets to be a little complicated. And so it's good to serve as a second problem. And for this one, we're given that we have two C10 by 15.3 steel channels that are placed back to back to form a 10-inch deep I-beam, essentially. The beam is 10 feet long, simply supported, and loading as shown. And so for the loading, there's a distributed load, 1,000 pound per foot. That would be the W that we're indicating on the previous page, that relationship between shear force and distributed load, W, and then a concentrated force, P, in the center of the beam. And if the maximum bending stress is not to exceed 16,000 PSI, that's what we're being asked to find, is what is that maximum load, P, that can be applied in the center of the beam. And so that's where this problem gets super complicated, is because the bending stress is a function of P, and we're trying to solve for P. So we really have to develop everything as a function of P throughout the whole thing, and then relate that to the bending stress with your resulting moment as a function of P times C over I. And so that's what makes this problem more complicated. And so if we look at that, we can find our I and S values. And so we will bring up that PowerPoint just momentarily. We're looking for the C10 by 15.3. I don't know if I can see that well enough to pull that up. Let's see if I can move this over a little bit. Expand this out. Well, that's a little bit clear. Can you read that, Jordan?
Yeah, I can see that.
All right, so we're good. And so the channel then is a C10 by 15.3. And so its I value is 67.4 as you go over there. And so since we're putting two of these back to back, it would just be double the area moment of inertia. And so we'd have I is equal to 2 times 67.4, or 134.8 inches to the fourth. And then S is equal to I over C. The full depth of the beam is 10 inches, so that matches what was given in the problem statement. And so S, you could look at that as I over C. We solved 134.8 inches to the fourth over 5 inches, would give us 26.96 inches cubed. And then if we look at S that's defined here, it would be 2 times 13.5, or 27 inches cubed. So both methods give us a S value really close to one another, just looking at those relationships between I, S, and C. But that's really kind of what I wanted to show from this table, is just pulling the I value off of there so that you'd have your area moment of inertia, and then how that relates to then the section modulus. When we get further along into the textbook, as you look more at the design of a beam, then this S will become more apparent when the geometry isn't given. We're finding that to be able to select a beam that has a sufficient S value, is where this becomes more relevant. But that's all we needed to know from that section. to get our I value for this problem. It didn't work. There we go. And so we have both I and S now. And again, for this problem, it's kind of convoluted. I'm going to go through it fairly quickly here because it's the same process that we did for the last problem. But again, it just starts out by solving for your reaction forces. There are no forces in the x direction, so A of x is equal to 0. Some moments about A again to figure out what Cy is as a function of P. And so one thing about that whole process of summing moments about A is we have a distributed load to contend with. And so with that, we do need to find an equivalent concentrated load of just 1,000 pound per foot times the length of the beam, 10 feet, would give us 10,000 pounds. So 1,000 pound per foot times 10 feet. And that would be located at the center of that concentrated or the distributed load area. And so that's why it's multiplied by 5 feet. We did that earlier, again, in the semester too, where you're finding an equivalent concentrated load based on if you're dealing with a distributed load like this that's constant, or even a triangular load. Again, that would be just the area of the triangle as the concentrated force, and it'd be located a third of the distance from where that maximum load is applied. But that's the process you want to go through when you're solving for your summation of moments, is find that equivalent concentrated load and then minus P times 5 plus Cy times 10. And you can then solve for Cy as a function of P and AY as a function of P. And so that's what we're going to find as we go through this, is that everything's going to be a function of P. And then if we look at the free body diagram as we continue on, I guess there's really two ways to solve this problem. The one way is to solve your moment out as a function of x, as we did in the previous problem, just making a cut here, and then going through that process to figure out where our maximum moment is. But with this one, we're symmetric on everything. We have a distributed load that's symmetric. We have a concentrated force that's in the center. And so a quick way to do this problem is just to realize, oh, our maximum bending moment is going to be in the center of the beam. And so this is the less convoluted way to do this problem, is just realize that is the case. And so you can draw a quick free body diagram of A of y. Your 5 feet of that first half of the section. Your 1,000 pound per foot would be active over 5 feet. So that would create a 5,000 pound equivalent force located 2.5 feet from the left-hand side. And then you would have your internal shear moment and a normal force. I used N this time because we have P showing up in our external load. But with this being the case, there's the P force occurring at the center of the beam. And so the way you can think about drawing this free body diagram is just think of the cut just occurring just a very small distance away from that center of the beam. And then you're not including that force at all, P at the center. And so if we do this quick, dirty way, we will find that the summation of moments at the cut is equal to M plus 5,000 pounds times 2.5 feet minus AY times 5 feet. And that, again, AY was 5,000 plus 0.5 P. And so we find out just instantly that the moment is equal to 12,500 plus 2.5 P pound foot. And so that was the less convoluted way to do this problem, just realizing that the maximum moment occurred at the center of the beam. And I put a little snippet in here then, sigma equal to minus m over s. We'll do that route. And moment then, again, 2.5 p plus 12,500, just switch those around, divided by s, 27 inches cubed. And then we have an issue with the units here being in pound foot. And so there's 12 inches and 1 foot will give us our maximum bending stress that we want of 16,000 PSI as the given. And so with that, then you can solve for P. One equation, one unknown will give you 9,500 pounds or 9.4 kip. And so that's kind of the quick way to solve that problem. But when I first lectured through that, I was trying to show how to do the shear moment diagrams on top of that and use the moment diagram then to identify what the maximum bending stress or the maximum moment was. And I think that got a little bit confusing. So it was probably about 4 to 5 years ago that I started showing this quick way to do the problem. And then the long way to do the problem is going through the route to draw your free body diagram and determine what your internal shear and moment is for that section. And so as you do that, if you cut between the left-hand side and where that force P is applied, you would end up with the internal shear and moment. You'd have your distributed load 1,000 pound per foot and the distance X. And so you could sum forces in the Y and solve for your shear, which is going to be a linear function with respect to X, also a function of P. And your moment then would be a function of X squared and P as well. V is a function of P, so that would show up. I guess one note on that is, again, when you're summing the moments for this, you do have to find the concentrated load. And so the concentrated load would be 1,000 pound per foot times our distance X. So that shows up in this first term. And then the moment with respect to the cut would be X over 2. And so we're multiplying it by the moment arm X over 2. And so that's why we get an X squared term in with that. But when you're drawing your free body diagrams and dealing with a evenly distributed load or a triangular one, those are really going to be, again, the concentrated force is going to be a function of the X value, and then the moment arm is also going to be a function of the X value. So that gets to be a little complicated with that aspect. And then same thing for BC, just drawing that from the left-hand side, keeping the datum the same. We will now have a P showing up in summation of forces in the Y. And then same thing when we sum our moments, we have to keep track of the 1,000 pound per foot times X times its distance X over 2. And we end up with a X squared relationship for our moment. And then when you draw the shear moment diagram, what we find is it starts out at 5,000 plus 0.5 P. It drops down to 0.5 P, then drops a distance P, goes to minus 5,000 plus 0.5 P and back. And so as you calculate the area under this curve, you get to the 12,500 plus 2.5 P for the maximum bending moment. And then as you're looking at that, the maximum p-value, you can pull that too from just plugging that in 5 feet for those two expressions for AB and BC. They'll both give you 2.5 P plus 12,500 as the maximum moment that's occurring there at the center of the beam. So you can get that graphically, or you can get that from the equations that you develop by plugging 5 feet in for those. And then we were back in the same spot where we were before, where we can then solve for that force P of 9.4 kip. And so I thought that was a little bit more convoluted in that our shear moment diagram is a function of P. So kind of keeping track of that stuff through, I think, was a little confusing for a first example problem, and serves a little bit better as a second example problem. I guess, Jordan, do you have any questions over this example?
It seems pretty straightforward.
Okay, yep. I think it's helpful, especially about 4 years ago or so, when I started showing the quick way to do it, because I think oftentimes from a design perspective and analysis perspective, you're looking at the quick, easier way to do things. You're less likely to make mistakes in those processes if there's a quick way to do things. And then looking at the more complex details, you get to have a deeper understanding of how those things vary as a function of X along the length of the beam. Because it's kind of interesting for this problem, you really didn't even need to know how the moment varied as a function of X to solve the problem. You just needed that intuition to tell you the maximum was at the center. So just draw a free body diagram for that first half and you'll be golden. This next page just kind of shows how that works out once that P value of 9,400 pounds is placed in there, just what the internal shear and moment are for that first section, and then for the second section. And so that gets you squared away there. And hey, we're all the way up to the 15th page now. And one thing we've kind of sidestepped today is really just that discussion on the area moment of inertia. We did define those for a rectangular section and a circular section. We're able to see that the appendices in the back of the book have those tabulated for common beams like a I-beam or a C-channel. But then there may be an occasion where we have to solve that ourselves. And so the first thing that I'll do is really show that area integral to get that BH cubed over 12 designation for a rectangular cross section. And then we'll use that on Wednesday and really talking and digging more into that discussion on area moments of inertia and how to calculate those quickly then for more complex sections. And so for this case, I am going to draw it with respect to kind of that reorientated frame of reference with X to the right and Y vertically upward, as they do with the textbook, as you find in the appendices. But I of X in this case is your second moment of area or your area moment of inertia. And again, remember that is just the area integral of Y squared dA. That integral over the area is just a double integral that you can do. Y squared dA can be broken down into dx dy. And so if we consider a rectangular cross section where our rectangle is placed at the center of the origin, and so in the x direction, this is our base, this be a positive b over 2 and a minus b over 2. And then for our height of h, that would be a positive h over 2 and a negative h over 2. when we plug in our limits of integration, then for calculating the moment of inertia about x, we would just have from the inside out b over 2 minus b over 2 and h over 2 minus h over 2. And so all it is just an area integral. And if we integrate the first inside expression with respect to x, there is no x value that we have to integrate. And so you would just see that essentially as a constant that you're integrating. When you integrate a constant, you would end up with that variable x showing up. So you'd end up with y squared x with that first integral. And substituting in your limits of integration, it would be a b2 minus a negative b2, which will give you a positive b at that point. And so you would end up within a by squared dy integrated from h over 2 to a minus h over 2. And so now when we integrate this second expression with respect to y, we do have a y value in this case. So y squared, when we integrate that, just y cubed over 3. Integrating polynomials is nice and easy, so we can all remember that one. So y cubed over 3 comes out of that integral expression, and plugging in our limits of integration, we have then h over 2 that we're plugging in here, but 2 times 2 is 4 times another 2 is 8. So it ends up being h cubed over 8 minus a negative h cubed over 8 as we plug in the limits of integration and realize that 2 needs to be cubed as well. And so when we combine this, that ends up being minus a negative, so plus, we end up with a h cubed over 4 times the b over 3 that we already had out in front, which gives us bh cubed over 12 for the area moment of inertia about the x-axis. And so that was just kind of a first step really to look deeper into our area moment of inertia. And it's just, again, the object's resistance to bending. And the higher the I value is, the lower the bending stress is going to be, and the less it's going to deflect. And again, for this case, if you wanted to look at the area moment of inertia, if you were bending about the y-axis instead, it would just be the integral of x squared dA. But in my opinion, it's just easier to reorientate what you're defining as the base and defining as the height if you're looking for the area moment of inertia about the y-axis. In this case of Ix, the base is this horizontal section and the height is the vertical section. If you're looking for Iy, you just flip those around. So the base would be the vertical section and the height would be the horizontal section. That's the way I always kind of did things, because then all I have to remember is bh cubed over 12, and I just define our the base and the height appropriately based on the problem that you're looking at. And so when we meet on Wednesday, then we can start looking at rectangular tubes where you're essentially subtracting off the area moment of inertia that's not present, with that being a tube. And so that'll be the start of our discussion on Wednesday, is looking at solving this area moment of inertia more for different geometries. But that's all we had for today. I guess, Jordan, did you have any questions at all?
Yeah, just on the when we're talking about versus on the x-axis versus the y-axis. So if it was, we're looking for the y-axis, that it would be twisting as it was on the paper left right.
Right, yep. And so for the y-axis, it would be bending in the left-right direction. And for the x-axis, it would be up and down
Okay.
about that axis. Yep.
Yeah, all right.
Other questions?
No.
Okay, I think we'll call that good then. And I'll get the PowerPoint added to the lecture notes. And then I'll get these videos uploaded as well. So thanks for your time and have a great rest of your day.
Thank you.